Thank you, appreciate it. I'll try to keep it somewhat brief, as I know you guys want to go for those tasty beers soon. Great, so yeah, a little bit about myself. I'm a software engineer over at Quantifind, leading our backend infrastructure team. I've been there a little over 2.5 years now. So brief outline of the talk, we'll talk briefly about what Quantifind does as a business. We'll talk about some of our technical challenges, various use cases that we have. We'll talk about some existing technologies that we've tried to solve for those use cases. But the bulk of the talk will be centered around some custom infrastructure that we've built at Quantifind to effectively address those use cases, and it's become sort of the main set of infrastructure upon which all of our data analytics products are built on. And we'll talk about some of the lessons learned if we have time. So what does Quantifind do? So at a high level, we're trying to find intentful conversations on social media sources like on Twitter and Facebook that correlate to a customer's KPI or key performance indicator, and essentially find anomalies between those two when you tie them together and try to surface up actionable insights. So if you look at the input from an input-output perspective, what's the input going in would be consumer comments, tweets on Twitter, comments on Facebook, and other data sources that we ingest, and third-party financial data in the form of a KPI that we actually get from the client. And what we output are the top-level actionable insights and interactive exploration functionality, which the custom infrastructure is directly supporting this ability to sort of interactively explore and ask questions about the data. So some of our technical challenges, it really boils down to this very large multi-terabyte annotated data set that we have that contains billions of comments, tweets, and other items that we've collected over millions of users, right? And we basically want to ask questions over thousands of different dimensions, basically flip the data around in various ways. We want to slice and dice very quickly over any dimension. And we want to perform some fairly non-trivial operations on this data set. We really want to ask questions at the user level. So one of the key themes of the talk is, a lot of times I think our gut reaction is to sort of pre-compute things or aggregate things offline in large Hadoop or Spark jobs, and then present sort of that pre-aggregated data set in sort of like a dashboard, and the user is only able to slice and dice as basically at that level of that you've aggregated the data. And then if you want to slice and dice in a different way, you usually go and update your Hadoop job and spit out some different type of aggregation. So just keeping the aggregation bit in mind as we go through the talk. So Quantifind does a lot of different things, but sort of one of the three things that we do that I'll talk about as use cases to have in mind as we go through the architecture, the infrastructure, are these three things here. So flexible time series generation, co-occurring n-grams, which sort of comes up a lot in machine learning, NLP type problems, and something that we call cohort analysis. And I'll go through each one of these. So, time series is essentially a time series of consumer conversations, of people commenting on a source like Twitter or Facebook or some other source. And so if you look at this plot, this is really just the frequency of conversations that are matching a particular date range and a particular set of keywords. So what we want to be able to provide is to be able to generate this time series, much like you would from a traditional time series type database, but we want to sort of take it a little bit further and be able to do sort of some custom logic, such as arbitrary date binning. We also want to do sort of user level deduping in different arbitrary periods. So n-gram co-occurrences, I'm sure most of you, given that it's a big data talk, you've probably come across n-grams in some form, but basically n-grams are just sliding windows of tokens in text. So one of the things that we do a lot at Quantifind as we're analyzing these conversations is to sort of break down the text into n-grams and perform all sorts of interesting algorithms on top of that. So being able to do this very quickly is important to us, to generate these unigrams, bigrams, and trigrams. So another motivating use case is cohort analysis. So the main example here is, let's say that there's a a release coming out for a movie, let's say Gone Girl. And what we'd like to do is essentially shine a spotlight over a group of users that are talking about Gone Girl, that are showing some sort of interest in the movie as they're reading reviews or whatever, and essentially be able to shine that same spotlight over that same set of users after the movie is actually released, so that we can do some interesting algorithm and further analysis on that same group of users. So we call that cohort analysis, just following the cohort over time. So I'll talk about some of the technologies that we've tried to, over my time at Quantifind to sort of satisfy to build our products on top of. So we tried Spark, Postgres, and Elasticsearch. So one of the issues with Spark is we sort of ran into some issues when we were trying to do our in-gram co-occurrences for very large data sets. Basically, just trying to generate these in a timely fashion was sort of troublesome for our 12-node cluster that we have at Quantifind. And what we found was it was pretty tough to reduce the search space of the entire data set. So what I mean by that is you sort of have your multi-terabyte data set sitting on disk, and unless you sort of manually put a certain slice of your data set in one directory and another slice in another directory so that you avoid having to look at the entire corpus, it's somewhat hard to do in Spark. Usually when you have an RDD over your full data set and you do a filter on that, it's still doing a full table scan, essentially, over every record when you do a dot filter on your RDD, unless you sort of tease apart your data set, like I said, in separate RDDs, which can be a little cumbersome if you have a lot of different dimensions, as we do. And at least for us internally, we have our infrastructure team and our data science team, and sometimes you collide with them with trying to run your Spark. Everyone wants to run their own flavor of their own Spark job, and there's some back and forth fighting of resources and frustration around repackaging jars and typical development, which also typical development challenges which also exist with Hadoop when you're trying to change your Hadoop job, how you have to repackage your jar and ship it across the cluster. So then we thought, well, what if we jam all of this data in Postgres, right? And so in Postgres, but have sort of table partitioning for the different dimensions. But what we found was it was nice if you were just querying sort of a small slice of your data set, but when you try to do things that would, sometimes you do want to do a full table scan, and that was very painful for Postgres. The query performance would just degrade. And trying to represent all of your business logic in the form of SQL queries is pretty limiting, right? If it's similar if you're going to use some other sort of like SQL and Hadoop technology. It's tough to represent all of your logic in SQL queries, and then if you want to add custom logic and custom functions, that's also a little cumbersome, right? It's kind of hard to bring the data close to the computation layer. We've also tried Elasticsearch, but we were essentially annoyed with trying to rebuild our indices as often as we needed to, as the business needs dictated. And it's still pretty tough to build that custom logic. Elasticsearch offers a lot of nice things, different probabilistic style querying and whatnot, but it's still pretty tough to sort of introduce some custom logic that you want, which we would always run into as we would build our products. So kind of like stepping back, we sort of asked ourselves, like, what do we really want, right? We want to be able to access our raw data, right? We don't want it to be pre-aggregated or pre-computed in some form. We want to access our raw data in memory and be able to address these use cases like time series, cohort analysis, and a bunch of other things that we do directly on the raw data in memory, because that is the fastest way to access your data, right? If it's all in memory. I mean, I think what a lot of users want or developers want is just all of the data sitting in memory so that you can just deal with it as quickly and as flexibly as possible. So we want these operations to be on the fly, sort of interactive and fast, right? We don't want to get into the habit of writing these batch jobs. So we thought, well, we want it in memory, but the one way to go about possibly doing that is just to pack it in a very compact binary form and just jam it into memory, right? However, that doesn't really scale, right? It doesn't really fit in a single machine, no matter how tightly you bitpack the data. So what we ended up doing was taking our compacted bitpack data and spreading it out across multiple machines and communicating across those nodes with Akka Cluster. What you can essentially do is take an HTTP request that comes into one node, and instead of that one node trying to make a decision, it just farms out that question to a set of servers that are communicating over Akka Cluster and hitting bitpack data sitting in memory, right? And then you get back your answers on the fly. So I think if you've done a little bit of Akka programming, or even just digging into how Hadoop works, this is essentially sort of an on-the-fly scatter-gather style type operation. So here's an initial sort of architecture diagram. So we have an HTTP handler that handles all of the incoming web requests for things like time series, cohort analysis, and n-gram co-occurrences for certain dimensions of this very large data set. And so it goes to the RTC Master. It farms that query out to the workers, which then send their partial answer back to the master to then be aggregated and sent back to the user. So each of the workers has a slice of this bitpacked data in memory. So digging into some more of the components, we have the pack file writer, the master node, and the worker node. So this pack file writer is really the only offline job that actually produces the bitpacked representation of this very large raw annotated data set. And it packs it in a custom binary protocol that we've come up with, and I'll give you some examples of that in a minute. And it packs it and organizes the data in such a way that it can be easily sent out and farmed out across the worker nodes in the system. So the master, like I said, handles the incoming HTTP RTC requests and routes them to the workers to sort of orchestrate that scatter-gather chain of events. And it basically tells all of the workers, hey, you're responsible for this set of pack files, this guy's responsible for that set of pack files, and that's sort of all the workers see. And the worker's job is to read those set of pack files from disk and jam it into memory in an efficient way. Excuse me. The other thing that the master does is it sort of has an adaptive caching layer that for very frequently accessed permutations or requests that don't change over time, it can cache those permutations so that it doesn't have to recompute a particular part of a request. The RTC worker through Akka Cluster discovers and registers itself with the master. So this is pretty easily horizontally scalable. We can just fire up a new worker and it sort of discovers the master and attaches to the master and asks for basically some work to manage a portion of those pack files. And then it loads its set of pack files into memory and handles the request from the master. So I'm not sure how many of you are familiar with Akka Cluster. But I mean, if you've done Akka programming before, it's a very nice continuation or extension of just normal Akka programming, of just sending messages to actors. Except in this instance, you're sending messages from two different JVMs, actors living in their own actor system in two different JVMs, and it handles. It basically can notify you when a node falls out of the network, falls out of cluster, or joins. It really sort of takes the pain away from that normal network-style programming that either we implement ourselves or we end up relying on Zookeeper for that kind of stuff. So let's talk about the compact data. So there's a custom binary protocol for the consumer comments and also their user records. Each of the records, if you're writing like a custom network protocol, the standard practice is to have a header which gives some information, and then you've got a body, and that's sort of the pattern that we follow, where we have a fixed header with a set of known fields and values. So this is sort of what it looks like. So you've got a 2-byte header. This is an example of one record that we would store. A 2-byte header, 8 bytes for a user ID, 8 bytes for a timestamp, and then you'll see that we sort of break up the text. So like a normal string that you would allocate, or that you would have like in a JSON record or even in memory, it gets a little tedious because you have to sort of go back to your C++ style days where you're keeping track of the number of characters and the number of bytes, and then expanding so on and so forth. Because we sort of are trying to be efficient with the space, we try to find ways to sort of store things in a more compact representation. So in the case of text, we can use a 64-bit zip hash for that, and then have a corresponding dictionary for that. So that in memory, you're just dealing with long values, and then if you need to go back to the string, you can then look it up in a corresponding dictionary for that. I don't have an example of that here, but we also have some fields that instead of using a traditional byte or short instead of using like an integer or a long, we can use a smaller dimension field for that to store different values. So we can sort of bit pack a bunch of Boolean values just in a short, for example, and be able to read that on the fly. So this is all fine and dandy. However, what we ran into, and I'm sure like as many people run into this, is the garbage collector getting in our way, right? So I'm sure all of us have experienced an out-of-memory error in the JVM. So JVM style programming is nice in the sense that you don't have to manage the memory yourself. You just allocate all these objects and you go crazy doing filter, map, flat map, collect, and all these things, and you don't really have to worry about objects coming, references to those objects. But when you're really trying to get the most performance out of your system, the garbage collector a lot of times can be your worst enemy and can get in your way, and can cause things like garbage collector pauses as it's pausing your system to try to look at all of the markings of all of your objects and seeing which ones can be released and which ones can't be, right? So this is where we ended up moving our system to off-heap memory. So I think this is something that you're starting to hear more and more about at conferences and whatnot. But the JVM really gives us this nice backdoor to like a C or C++ style means of allocating memory using unsafe. So this is currently like a hidden reference in the current JVM. I think in Java 7 and 8, you have to use reflection, I think, to get at it. But I think in Java 9, they're actually going to put a proper public interface to get access to these underlying utilities. But it allows you to do C or C++ style malloc operations and be able to sort of, request from the operating system a chunk of memory to use for things, to store things in. The only downside is, well, it comes at a cost in the sense that you have to manage that memory yourself. You're literally just getting a chunk of memory that the garbage collector is not keeping tabs of, but you're responsible for how you lay out your data in that off-heap memory, and making sure that you release portions of it if it makes sense, and all of that comes with our old days of C and C++ style programming. So this was the same diagram from before, but the packed data, the green boxes at the bottom, have been replaced with off-heap data. So each of the workers will load their slice of the pack files, but store them in off-heap memory, and so they're managing that. So working with off-heap data is a little different from like normal JVM style programming. You have a reference to this unsafe object, which gives you sort of access to this black box of memory that you've allocated. Excuse me. So for example, here for a timestamp method, normally we would just have a long that's part of a case class, for example, right? But in this case, what we're doing is we don't have that because it's not materialized in the JVM like it normally would be. So here you have a reference to your unsafe object, and you're saying get long. And when you have a reference to this, you actually have a reference to the starting memory address of the block of memory that you've allocated. So when you say here get long 2 + 8, I'm just being explicit and I'm saying skip past the 2-byte header, skip past the 8 bytes of the user ID, and then put me at where the timestamp falls in that protocol that I showed earlier, and extract the long value. And if you see here, it's a def, right? It's not a val, because moving to the primary goal, we never want to materialize data that we don't have to materialize, right? We really don't want to throw objects on heap for the JVM to have to manage if we don't have to. So this timestamp will just sort of be sitting in off-heap memory and will only be extracted when you call this method. So we really, just going back to that, we really don't want to materialize things that we don't have to. And this becomes really important for things like strings, because strings living on heap will take up more memory when they're represented on heap. So just, don't worry, this is a bunch of code on the screen, but don't worry about getting too much into the details here. But even things like off-heap, like binary searching, right? Most of us use Java util arrays binary search, and you have a materialized array that you're passing into it. But that's really sort of off limits in this style of programming, right? So in this case, the binary search method, you have, you're passing your unsafe reference to your off-heap memory, and essentially the bounds in off-heap memory where you want to do your binary searching. So the key thing really is just like the val term equals unsafe.getLong. That's where you are actually pulling the value to compare. So that's kind of like the main thing to sort of look at, where you would normally just do an array reference lookup. Here you're doing an off-heap lookup. So I mentioned the search space earlier. The search space is actually really important for us because for a lot of our queries, we may only be interested in a particular facet, like a particular client or a particular date range of data. And making sure that we don't do full table scans where we don't have to is actually really important for us. And so what we basically ended up doing was creating these facets, these facet indices. So these are custom facets that are represented as tree maps or they could just be arrays themselves, but they're essentially just locations to offsets in off-heap memory that pertain to a particular facet that we care about. So it could be a particular time of day, it could be like a month or a day, something like that. So if you're only querying for things that happened within one day, you can very quickly ignore all of the other data that's in the system. And this is important because whereas this system is not getting thousands of requests per second, it's getting few requests, but in a single request, we're trying to really do millions of operations in the sense of visiting millions of records. So if we can avoid visiting 1 billion and instead just visit 1,000 that would potentially match, then that's a huge win for these types of queries. So extending the architecture diagram again, so each of the workers has their off-heap data that they manage, but then they also have one or more facet indices that are essentially pointers into the off-heap data. So here's an example. I kind of touched on this earlier, but most of our queries care about a particular time range. So then how can we avoid searching over every single record when we only care about an hour or a set of minutes, for example, something like that. So what we can do is we can build, as these workers are loading their data and shoving it in off-heap memory, they can build up these indices. So in this case, it could be a tree map of a long to an array of long, where the keys are, so I should step back a little bit. So when you start doing things like this, when you start using these normal data structures, they do live on heap. And so the indices live on heap, the data lives off heap. So in this case, the keys are the timestamps, the rounded down timestamps, and the values are offsets to the off-heap records for that particular time. So when you want to do operations like a set of days, you can do login style range operations on this tree map data structure to get back very quickly which offsets you need to look at. So in this case, you're preventing from just having, you don't have to search all the arrays of longs that are in this tree map. You only pull back the ones that could potentially satisfy that facet of the query. So once you have this array of long offsets that you want to visit, right? How do you sort of traverse this array as quickly as possible and do the computation? So this is where within each of the workers are multi-threaded. So the worker will find which array of long offsets could potentially satisfy the query. And then it just fires off a bunch of additional sort of mini-style worker threads to tear apart or to traverse this array. So one thread might do a certain number of offsets, another thread might do another region. And so the workers themselves are answering questions in parallel, but then within each of the workers, there are like mini workers that are slicing and dicing the arrays and doing a mini style aggregation to be sent back to the master. And we found that this helped out quite a bit, as opposed to just plowing through the offsets one at a time. So I'm not sure if you guys have followed Kelly Summers, but she tweets a lot of great things about infrastructure and she's really big into like testing a whole bunch of different like open source technologies and giving her comments on that. So she tweeted something which really caught my attention one day. I hear about how immutable structures are awesome, but here's the thing. You want millions of operations a second, you need to stop allocating memory. So this was one of the key things that we learned, that for our requests and to return back in a reasonable amount of time and to not piss off the garbage collector, we had to really keep an eye on our allocations. So that's really what RTC is about, is limiting the allocations to satisfy a query. So some of the lessons learned, I keep talking about this: reduce allocations as much as possible, avoid allocating, I'm like 90, 100 gig JVMs that have many objects that are stuck in this tenured generation. That's just really not good for the performance of your application. And the expensive data that you've calculated or that you've answered can be kept around in LRU caches, and that can improve subsequent queries so that you don't keep repeating the same amount of work. Now, if your data changes frequently, that's kind of hard to do, but in our case, the way that the cadence of refreshing our data, this LRU cache mechanism helped out quite a bit. So another thing that we so kind of adding on to this LRU, so most LRU caches, right, the way they work is, they're essentially bounded, and then when a new element needs to come in, you evict the element that wasn't used the most. However, there are cases where your LRU cache may be holding very expensive objects or very large objects, and you may not be putting something into the cache. But the JVM is experiencing pressure, and you would like for it to evict that element out of your cache for you, instead of waiting for the next request to push something out. So one of the things that we learned is if you wrap your values in soft references, and that sort of tells the JVM, hey, I would like for this thing to be around if it can be, but if not, feel free to just evict it for me and allocate the memory. So this was something that helped us improve the stability of the system. A couple of tricks, just chunking very large requests into smaller requests. That sort of goes into the workers having yet more mini workers to plow through things. Scala collections are great, but for certain operations that we were doing and certain, when we analyzed the memory, we found that just using trove collections or even just dropping down to primitive arrays really brought us to the next level. So. Almost done. So was it worth it, building a custom solution? We definitely think it was worth it. We really tried to use these other, open source technologies, even other ones that I didn't mention here, to sort of satisfy the use cases that we have for the types of products that we're building. And what we found, some of the core benefits is, the business guys might come around with some, or even our data scientists might have some idea for some really cool new algorithm that has some various performance challenges. And the first thought is, okay, how do we make Spark do this, or how can we think about the problem the way Elasticsearch would want us to think about it? Because we own the system, we can just go right in and come up with an implementation for that query that is like squeezing out the most performance as possible. So we can adapt to changing business requirements, and we've addressed some of these things already in terms of further improvements, but we want to add more redundancy. A lot of this just comes for free when you upgrade to. We're using a bit older version of Akka Cluster just because we have like Spark and Akka Cluster in the same SBT build file, so sometimes they clash. We might want a newer version than what Spark would build in. So we're working on teasing those things apart so we can add more stability by getting some of the improvements in future versions of Akka Cluster. So in summary, the whole system really boils down to Akka Cluster being there for the network communication, using non-aggregated off-heap data. So the key thing there is to remember that these records are in their rawest form. They can't be in any further broken down form. It really is an individual record that you then do arbitrary ad hoc style interactive querying over. And just keeping an eye on the way that you write Scala code to try to be as efficient as possible was a win for us and for the product. So thank you, and of course, if any of this stuff is interesting, chat with me afterwards. We're also hiring. Thanks.
Thank you, Ron. I think we've got plenty of time for questions.
Did you at all consider utilizing Avro in place of a custom binary format?
We did. We tried, we looked at a few. We looked at something from Google called flat buffers. We looked at Avro, we looked at things like message pack and things like that. And I think the issue with, at least with flat buffers, it was a couple of us trying these different things, but when I looked at flat buffers, I think what was happening there was the fields, they allow you to specify these optional fields. And so I think they end up allocating like a short, I forget what it was, a short or something else before each of the fields. And we couldn't really find a way to stop that from happening. So what we found was we could be a little bit more efficient with our own custom format than by using one of the off-the-shelf libraries. But I mean, that is a piece that could definitely be replaced by some other open source library. But we ended up, we only have like 2 or 3 different schemas, so it's not a huge maintenance nightmare. But if we have a bunch of them, we'll want to revisit using something that allows you to just do some sort of high-level schema and then generate that efficient code. Hey.
Ryan, it's a great talk. I got a question on the Akka side. Actually, I got 2 questions. Sure. One is on the Akka side. Is do you send the message you send? Is it large or is it small? So that's my first question.
Yeah, sure, right. So we have run into some issues where the results can be kind of large, but we ended up turning on the protobuf serialization and compressing it a little bit, and basically enlarging that frame size, that tuning parameter that Akka lets you tune, and we haven't hit any issues of going over it. But yeah, it was a slight annoyance in the beginning where, especially in some of those n-gram co-occurrences, those can be large data sets coming back. So
yeah, we're hitting the same problems because they changing the buffer size and they also increase the memories. And
yeah, right.
My second question is, you're using unsafe for the off-heap memories. Notice that Spark's tungsten projects also do exactly the same thing. So laying out their own memories and using unsafes. So
right.
With that approach, are you thinking Spark can solve your problem? Partly.
Yeah. I mean, so I mean, I should mention, like, I mean, we're still like fans of Spark, right? Like, we still use Spark. Our data scientists still love using it for truly ad hoc style, like Spark jobs and MLlib and things like that. Yeah, it was kind of funny. Like, we implemented the off-heap change to RTC, and then later one of my friends sent me the article about the, what is it, Tungsten, Project Tungsten, right? And so, yeah, I mean, I support like all of these open source projects evolving, and I really would love for some generic solution to be there to satisfy all business needs. But, like as you saw in the previous talk, like the Flink guys, they think that they can differentiate in some way, and everyone wants to do a different spin on these things. So what we've built is custom, tailored to us. It would be really hard to open source it. I think some of the ideas are open sourceable, if you can open source ideas. I don't know, like approaches, like these are things that you guys can use in your own products and things like that. But yeah, I mean, it would be great if there was some silver bullet that would implement everything, with all the different use cases that we have. Yeah. Anyone else? Yep.
Yeah, so I have 2 questions like everyone else, right? So the first one is, have you guys created, because what you are describing there is a great approach, but for me, it looks like a nightmare for scalability. I mean, if your company grows like 1,000,000x or 100x, right? Like maintaining what are the resources, not resources, but what are the things that you guys are doing in your code base to actually think about that scalability, right? Because off-heap memory sounds really cool, right? But we all know why we are not writing C++ code anymore, right?
Yeah.
So that's my first question.
Yeah, sure. Yes, I can answer that. So actually the bit of unsafe code that's going on in our system is really probably about maybe a total of like 100, 150 lines, something like that. So what we've done is we've put these views on top of this thing, right? So if someone new were to come and develop on top of the system, add new functionality, they don't have to know about unsafe or off-heap memory or any of that stuff, right? Because they're just using a plain Scala object that has methods on them, right? So like a time step method or things like that. So if you're modifying the off-heap, the way you represent data off-heap, then sure, you have to manage that. And we have a pretty good, we're only like 4 or 5 infrastructure guys. We all know that code base pretty well. And keep in mind, it's custom to us, so we're not so in terms of like scalability, there's the scalability of the project itself from a code perspective, which we haven't had any trouble adding new features or anything like that because Off-heap was holding us back or anything like that. And also just from a performance perspective, it's a horizontally scalable system. So you just fire up new nodes and then the data gets spread out more evenly, and from a performance standpoint, that works. So I think that's what you were asking, right?
Well, I was asking more like you're saying you're 4 guys, and I've been there. I know what that means, but I am also in a team right now. We are 150 engineers, and I can tell you, it's a pain to maintain a code base by 150 engineers when you have one guy doing memory allocation all over the place and another guy trying to deallocate. But that's not the point.
Yeah, I don't think it's as scary as you make it sound. I think with pull requests and
Yeah.
GitHub and everything,
Of course. I mean,
you just have to be a mature developer, I think.
Of course. Yeah. It's all about the organization,
Yeah,
right?
right.
And my second question is, why did you guys consider something different from Scala? I know this is a Scala conference, sorry guys. But what I mean is like, well, you're saying like we have all these problems with JVM and whatever, and these strings are a pain. Like why use Scala? Why not use like, I don't know, C++ or Java or something that allows you to have more control? Because for example, Java 8 allows you to do memory allocation and deallocation manually, right? You can actually do that. You can do off-heap memory allocation using Java facilities, right?
Right.
In Java 8.
Yeah.
So why keep using Scala?
Yeah, so that's a good question. I think it definitely did cross our minds just to go straight into C, C++ implementation of it. But RTC is one bit of infrastructure of a much larger stack, right? And so what we found was if we could like tuck away this off-heap low-level memory management stuff into like a small module, but then the rest of the code base actually benefits a lot by just being written in Scala because of the high-level things. So not all of RTC has to be done this way. There are many parts of it where we actually really enjoy having Scala collections, especially once the hard work is back going to the master. So in the worker side, you want to be as efficient as possible, right? Because those are the guys that are doing all the hard work. But then once the responses come back to the master, the way that you aggregate and the way that you do further computation on top of that, having Scala and its collections actually is really great because you don't have to be as performant there because the hard work was traversing those millions or billions of records. So if you can minimize that, then it gives you more room to have fun with the Scala collection. So if we had to write all of that in C or C++, it would be annoying, and it would be sort of this piece that didn't integrate very nicely with the rest of our system. But we were a Java-based company in the beginning, and it was sort of through Spark that we transitioned and sort of fell in love with Scala. Yeah.
So your use of the off-heap stuff it's only read-only, right? It's read-only, correct?
That's right, yes. So RTC itself is this, it's read-only and it's sort of this immutable thing, right? There's no notion of like a session where you can update, create your own table, kind of thing like that. It really is just solving our specific needs.
It's read-only. Yeah. And so you're actually making a copy of bits of it as you need them, correct? You're materializing them, as you said.
Yes, right. So in the cases where we have to do things with strings, like use methods on the string object, we have to materialize that. We have to bring it from that byte representation and instantiate a Scala string. But we try to minimize that as much as possible.
You should be able to put a mutable string directly on top of the data.
Right. Oh yeah. You definitely can. Just like we did the binary search completely off heap, you can start building even more data structures or more views directly on off heap to minimize that. But it kind of goes back to the question that the guy asked earlier, where it's nice to have some of the niceties of the JVM and Scala, and if you can handle a little bit of performance degradation in those little areas, then it's kind of nice to just write some simple code to do it. But yes, I mean we do have other things where we have bit sets that are just off-heap bit sets. They're not like the Java util bit set or things like that. So where we have to write off-heap data structures, we use that.
Okay. We have time for one more question.
Yep. Hi.
Do you have any performance metrics surrounding the whole half-heap implementation that you guys do? Or are there any literature surrounding that whole half-heap? It seems very interesting. So I was wondering if you guys have any numbers or performance gain with the.
Right. Oh, you mean, yes, like doing certain operations in this new system versus the older one? No.
Specifically with the half-heap thing. So.
Oh, specifically with off-heap?
Yeah.
No, so the one thing to keep in mind with off-heap is that it's not that off-heap doesn't necessarily give you faster performance, it just lets you store sort of a lot of data in a JVM kind of thing, right? So when you go from like accessing an array that's on heap, doing array indice lookups is actually faster than actually going off heap and doing that. Like if I wrote the binary search method just comparing it to the Java util one, that one should actually be faster than the off heap one. It's just that the off heap lets you have a ton of data loaded in memory that is at your disposal, whereas if you tried to like shove all of this data in like a Scala hash map on the JVM, you would quickly run into all sorts of hash map resizing and the garbage collector getting in your way. That's really what drove us to off heap, was because we really wanted to use the memory as efficiently as possible. But I'd have to do more research, but I think going off heap is just a slight performance hit. But on heap, I believe, is generally known to be faster. But if anyone knows better than me, correct me. But I believe that on heap is still faster than off heap because you have to cross that boundary out of the JVM, or pseudo out of the JVM. I mean, it's still, if you look at the process, it's still the JVM process that has all of that memory allocated. It's just that the garbage collector doesn't see it. Yeah. Cool.
Thank you, Ron.
Great. Thanks, guys.